Good morning, all the participants. Welcome back to FTP on Bio-Inspired Computing for Data Analytics. Respected Dr. E. Damodar Reddy, sir. Welcome, sir, to the session.
Yes, thank you, madam. Thank you.
Today's first session is on human-computer interface using machine learning. I request the sir to hand over the session.
Okay, madam. Thank you. I'm sharing the screen.
Okay, sir.
Can you see the PPT? Please confirm.
Yes, sir. Yes, sir.
Yes,
It
sir.
is visible.
Yes. So, good morning, everybody. This session, we are going to talk about the other type of bio-inspired computation model. We are going to take a case study like human-computer interaction. Then we are going to see how we can use this for some various real-time applications. Right. So, let the session be interactive, and in case you have any doubts, please feel free to stop me. So now when we talk about human computer interaction using machine learning, so please now try to tell me what is the main purpose of this human computer interaction. I'm going to formally define this anyhow, but just try to understand. See, when you are working in any of your respective research domains, what is the first problem you have faced? Tell me, any one of you. You are into wireless sensor networks, cloud computing, information security, some other network related problems, whatever it is, wherever you are working on IoT. What is the first problem you have faced? Tell me, somebody. There is a common problem in any research domain when we are investigating in some problem. Tell me, anybody?
Understanding.
Pardon?
Understanding.
No, understanding that is anyhow, that's the common problem. But what I'm asking is, when you are starting working on a particular problem statement, when you are going
Not
to
able to get whatever we required.
can you elaborate, madam?
That means
What
we
about
search,
data? What
we
about
think
data?
of one aspect.
Whether data is available to you?
That means we are not able to get whatever data we want in our what we are thinking.
Yes, so the data collection or data availability is the main problem. Wherever you go, you are working on some load balancing problem or energy efficiency, clustering, clustered selection, routing, localization in wireless sensor network, some security problem, some ideas, intrusion detection system. Anywhere, wherever you are working, some other cloud computing, hypervisors. This common problem like data collection or data availability is one of the problem, because nowadays there are plenty of open resource data sets are available, but still they are very limited, their sizes. If you want the full data set, then you have to pay some money or whatever it is. Getting a data set is one of the first problem which you face. So unlike the other domains, now in this domain like human computer interaction, okay, by just name we can say that human computer interaction, what we are trying to do here, we are making an interaction or interface or a channel or a communication between a machine and some human. When we say human as a whole, we refer some part of the human like brain computer interface or some heart computer interface, heart computer interaction, whatever it is. So this type of interface or connection, when we establish the communication, once it is started, we are going to understand something about the behavior of the thing which you are connecting to a machine or a workstation or a computer. Then you get data, because the moment there is a communication is established between two things, we can generate some data, right? Obviously. So the problem which you are facing in every domain is solved in the very beginning of this domain, human computer interaction. Do you all agree that data availability, the moment I make a communication between these two, like some part of the human body and a computer, a workstation, I get large amount of data, right? Do you all agree with me?
Yes, sir.
So the problem in other domain is the beginning in this domain, like the solution to that problem is the beginning in this domain, human computer interaction. When you are making an interface between a computer and a part of the human body, like you see, you must have heard about like ECG recordings or EEG recordings, right? Now what is this ECG tells about, you tell me. ECG data.
Heart,
Somebody tell.
heart
Yes, the
function.
functioning of the heart and any complications for further could be arise, and what is the
Yes, sir.
current state. Many other. When we draw some polygraphs, some kind of graphs, real-time graphs based on the heart functioning, we are going to analyze the graphs and say that there is something problem with the heart, or everything is fine. The recordings are there. There is something abnormal anomaly recording is noted, something like that. So we are making an interface between the heart and some machine, some computer, some workstation, whatever it is. Thereby what happens, whatever the data you are collecting from the heart, you are going to plot on the real-time screen and going to analyze, make some analysis over that. Fine. So by doing so, we are getting something. What we are getting, some understanding about the connection which you are, about the thing which you are connecting to a computer. So a lot of data, first and foremost, the data is in your hand. That is not the final solution we are looking at. First objective is human computer interaction. We are getting a lot of data into our hand using that. Now next thing is how to use some machine learning model and how to use some bioinspired computing model, some genetic algorithm, what and all, the advanced machine learning model for the problem which we are investigating. Now if you take that hard computer interface like hard data, ECG data, I'm going to predict what some predict the heart attacks, cardiac arrest, or somebody has already attacked with a heart attack. What is the possibility that it could be again recurrent, again the heart attack may come? This type of analysis, or be any abnormal behavior is noted with the functioning of the heart or brain, whatever it is, right? So when we make such an analysis, we'll be able to make all these real-time applications, some prediction, some detection models, and all those things. Do you all agree?
Yes, sir. Yes.
Yes. So now the purpose, the definition is what I will define: human computer interaction. We are making an interface between a computer or a workstation and some part of the component of the human body. And the purpose I have seen for some real-time application like prediction of some heart attack or whatever it is. When we talk about heart, if we talk about brain, there is some other. So when we say whole human computer interaction, it is referring to what, like brain computer interface, or heart interaction, what we are making, or eye to eye interaction when you are making many others. According to the thing component which are connecting in the human body to a computer, the application gets changed, right? So, but using some machine learning model, when we say why, because when you take large amount of complex data, real-time signals, some incremental data, obviously you require some machine learning model. Do you all agree? Now, when we talk about some brain computer interface, for example, first of all, let me formally define what is human computer interaction. Then, like I already defined, there is a, here the problem is how to establish such a communication, what type of hardware and software is required. It is not only hardware, it is not only software, both are required. Why? Because when you are establishing what type of interface we require, what type of electrode wires we require, what type of hardware, sophisticated hardware we require. Because to connect brain signals, we require some kind of hardware. To collect a heart signal, we require some other kind of hardware. To see the behavior of the eye, we require some other hardware. So obviously, it changes from your component to component. Okay. So now it's a formal definition. Can you see the definition of human-computer interaction? Can you see the slide? Please confirm. Hello?
No, the slide. This is again the first slide only. We cannot
First
see the
slide.
definition.
1 second. I'll share the
Yes.
entire screen.
Yes. Now we can see.
Let me just share the entire screen. 1 second. Can you see it now?
Yes, sir. Yes, it is visible,
Yes.
sir.
So now we already defined like human computer interaction, which we are trying to define as a kind of dialogue or a communication or an interchange or between a computer or a workstation or any machine. And our job is how to capture such a behavior from different channels, different locations of the human body, and how to exchange different actions and intentions. So the whole paradigm is defined like this. Now, when we refer, it is an interaction or interface between humans and computer. First, we need to identify the application where we are investigating with, and we are going to work on identifying this what type of signals we are recording and how to pre-process the signal. Then, what type of machine learning model we require is all. So when we talk about this human computer interaction, it is not only just using some hardware, it is like considering with design and then evaluation and implementation. Normally, this we call as a kind of interactive computing system. Why? Because this is used for some interactive communication between a computer and a human part of. Obviously, this we can define as an interdisciplinary field. Why? Because now it has different applications where considering which type of interface you are making between a machine and some part of the human body. So obviously, a lot of real-time applications, interdisciplinary applications is not only some security or defense or some forensics or psychologist applications, many other we have. So the same thing like which is very interesting. We use in cognitive psychology, neuroscience type of application, and other sociology, sentiment analysis, linguistic, other type of applications, economics. So the crucial part in this particular domain is first we need to identify the human or the component of human. That is like whether you're making data or whether you're recording data from human brain or heart or whatever it is. So human, when we refer human, we are going to identify which application we are going to refer within a human. Like if the brain related data, we're taking some application, and say similarly some other application when we talk about different component of the human body. Computer, when we refer, say what type of hardware computer or you can say hardware equipment we needed to deal with the signals that are collected. So some high-end workstation you require or some other high-end machine you require, we are going to identify. Third is how the interface can be made, what type of channel establishment, what type of electrode wires you are using, what type of electrode gel we are applying, what type of amplifier we are using, all this hardware in between these two. So one is one vertex or one endpoint, other is other endpoint, in between what and all the edges we have. It is like just a communication between it. So the main purpose of this is to make such a interaction possible and getting some applications. Now, first and foremost, why do we need to understand this? Because see, obviously, when you are going to use these bind-speed algorithms and then you deep learning models, genetic algorithms and all, first and all, we are going to identify some application. After that, we are going to decide what to do with the application or how to solve the applications. Obviously, we are going to identify suitable machine learning model. But first and foremost, first of all, you have to understand why we are studying this interface to a human and a computer. Why? Because most of the interacting technology which we are using, like with respect to human, it is like cognitive when we are talking about with the human, whereas in case of a conventional machine or a computer, it is different. So when we are trying to upload or dump the cognitive behavior to a workstation or a computer by just taking the data from the human part, this type of cognition analysis or you can say some understanding we are going to make it. It's not only brain computer interface, everywhere. There are plenty of other applications that can be solved with the deep learning type architectures or any other. Hello, any doubts? Please mute yourself unless you have any doubts. So now, what do you mean by this interaction or interface? Like I already mentioned, we are going to identify what type of hardware we require. We are going to identify what type of software tools we require. We are going to see what type of other amplifiers and then these recording analyzer software which we require. The entire setup we need to understand how to communicate and use it for some. Sometimes this can be change intervariably. Interface and interaction, there's a difference. Interaction, when we talk about mainly communication oriented. Interface, when we talk about working on the hardware requirements. So both are same almost. Interface is needed for the interaction, human computer interaction. So they can be interchangeably used. So the basic purpose of all these things when we talk about the plenty of applications are there, which we see now in the next slides. So now I will ask you, if you are working on some type of human computer interaction, say system, like I will talk about a brain computer interface, assume that. Tell me if you can integrate or if you can interface or communicate a computer to a human brain. Tell me what type of applications we can derive. Anybody? Heart, I have just highlighted. You can predict the heart attack early detection of the heart attack, and then identifying the functioning of the human heart. Similarly, if you go with the brain computer interface, because there are all some kind of bio-inspired computing models, right? When we talk about human brain is a
Brain.
biological organ, right? Human brain is a biological organ. Obviously, they all come under kind of biological computing models. So when we go with the human brain type architecture, just tell me can you give me some? There are plenty of applications like heart with the brain communication. There are plenty of applications. Can somebody tell me one, two?
We can identify the tumors.
Yes, that is one possible. When we take the brain signals and all, some portion of the brain, wherever there is some signal, is not, not properly inhibited or captured by the source of
The pituitary gland functioning, how far it is releasing the hormones and all we can observe.
yes, functioning as obviously, because the moment we make communication, we know its behavior. We can
Yes.
compare with the normal brain functioning and see there is something. So obviously that is possible. You are right, but other than medicinal, any other application can you tell me? Simple application so that we understand.
You can find emotions of a person.
Yes, emotional, or you can say mental state analysis or emotional classification, behavioral analysis. All these things you can do, right? Any other applications? Any other application?
Can get EEG, electroencephalogram.
Easy only. I'm talking about some brain signals I will take. With the brain signal, what and all the applications we can do.
Stress levels.
Yes, finding the mental state analysis, or you can say the stress levels, and yes, that is one. Any other?
Sensory organs nerves, we can check the functioning of sensory organs nerves.
Yes, that conventional, that central nervous system, how it works, what are the sensory motor patterns that can be analyzed. So similarly, there are plenty of other applications like please turn off your microphone, all of you. If you're speaking only, then turn on. Yes. Now, similar to these applications, there are like I can generate IQ of some person. Normally when we refer to IQ, which part of the human body is responsible? You tell me. When we talk about IQ of a person,
Brain.
brain, right? Obviously. So if you take the brain signals, maybe I'll be able to develop a model based on my brain signals or functioning style. I can say this is my possible IQ levels, and then similarly lie detection. When say somebody is lying, which part of the human body is responsible for lyness? You tell me. When somebody is lying,
Yes,
Brain only.
brain only.
brain obviously. When somebody is lying, it is only the brain is lying actually. When we talk about, so we can say lie detection, lie detectors we can develop. So it's a BCI like
Think our
signals based lie
ability also we
detectors.
can
Pardon?
thinking ability of a person.
Yes, yes, same. The smart thinking about the behavioral analysis, everything we can make. And similarly, lie detection, and then human contemplation, behavior analysis, emotional classification, mental state analysis. And similarly, if you go to medicinal side, like we already somebody talked about some brain tumors and all. Similarly, like if there is a paralyzed person or locked in a immobile person, means who cannot move or walk, but his brain is working normally. Maybe he can control the outside world. Nowadays the dream of the world is like controlling entire thing in our premises with a by just sitting on our chair. So obviously, what happens when we have a paralyzed person who cannot move or walk? Obviously, what happens if he can interface his brain with some some smart home appliances like AC, fan, light, and everything. He can control the entire surroundings by his thoughts. Okay. So obviously, because when you want to switch on the light or switch off the light, obviously it is because of your thoughts, right? So when you're controlling the real-time world with your thoughts, that is one of the real-time, high-end application which you can perform. And similarly, in some forensics defense applications, it's only samples. Plenty of applications like that exist in the literature, or they're going to be evolved in the near future when this type of BCS systems of high-end nature are evolved. Okay. So now when we talk about biological computing model and then other, first we have to understand. Now you see uh, how the artificial neural models are developed. You tell me. We have understood the biological neural model. We have understood its behavior. Then uh, we have developed a computing model, how the central nervous system works, how the sensory organs take input, and how the motor organs processes that, and then how the neurons communicate accordingly. Everything based on the biological neuron model functioning, we have developed artificial neuron model. Fine. So here what happens? If you see the computing world nowadays, most of the problems are being investigated with the neural networks. Yesterday, I think we have highlighted the advantage of neural networks. Wherever there is some supervised nature of training is given to you, obviously we'll be able to use neural networks. Why? Because they're very effective whenever there is sufficient training is given. And if there is large amount of data and some good amount of handful amount of label data you have, like deep learning type architectures are more suitable. The advantage with deep learning type architectures is what, how long you are, how much increment in data, how much growth in the data we have. Still there is growth in the accuracy of the model. Why? Because of the iterative learning process. So if you go with these type of models where we are going to understand how the brain functions, and we can develop some high-end sophisticated applications better than conventional neuron models. Why? Because you see, we have observed just how a neuron cell communicate to another neuron, then how the behavior is captured, and accordingly how the computations are made. Nowadays, artificial neural models are ruling the computing world. If you have a small amount of training, they can perform exceptionally good. So they're like a boss, this computing world, artificial neural models, artificial neural networks. Now, if you see just one neuron communication, if you can provide such a complex or useful applications, if your entire brain functioning, if you can understand, and you can propose such a high-end model based on the brain functioning, obviously that can, give even better accuracy and better details with any computing problem, right? So here we have to understand the functioning of the human brain. This also conduct bio-inspired computing model because it's a human bio-inspired. Obviously, when we talk about, we're going to understand how the neurons work and what type of signals they emit and how do they communicate. Normally, each neuron traces different electrical inputs from about 1,000 other neurons. Normally, now when some impulses are being generated or added, and finally they are causing to some electrical discharge or a signal which we call as action potential. Then these action potentials try to be captured in the form of some electrical signal, or you can say whatever you call some kind of EEG signals, whatever. Yeah? And normally the speed of this type of signals is like one neuron to neuron. I'm talking about this action potential is at light speed, or you can say around 250 miles per hour. Then you can imagine with such a light speed, when such an electrical signal is being generated in the human brain, if you can capture such a behavior possibly and use it for some real-time application, what and all we have talked about, various applications like light detection, printf applications, everything. You've already seen how the central nervous system works and how the behavior can be captured here, right? So you should understand same way how we can use these applications using some complex brain understanding. Please try to understand, just a neuron to neuron communication, we are coming with a complex artificial neuron model, deep learning, extreme learning machine, and so on. So CNN models. Similar way, when we go with this type of entire brain model, like if I take a whole brain as a computing model and develop such a complex similar model to artificial neural networks, it will perform even high-end operations, like a difference between a workstation and a supercomputer, obviously. Are you following me? So our job is to use such a complex biological behavior of human brain, and by using human computer interaction we collect the data and then we use it for some real-time application like this. Because already you must have understood how the neuron communication happens and how the neurons behaves here. So it's very important to understand this type of complex behavior from the human brain. Now, just to hold on, I will play some small video. Can you see the video? Please confirm.
Yes.
So
Yes,
just
sir.
observe. I don't know whether audio will be, coming or not. Just you can just observe the video. I'll explain later.
It's not visible, sir.
I'm playing now. Just check once. Can you see now?
Yes, it is visible, but on audio is not there.
Audio, I think there is some issue, but anyhow, I'm playing a different computer. That is the reason. Can you see the PPT back?
Yes, sir.
Yes, I think there is some
Yes,
audio. I don't know whether video was clear or not. Now let me explain. Now when we talk about this bioinspired computing model and this new neuron models and all, first of all we should understand how the neuron communication happens in the human brain. Now if you see, if you're touching a hot object, the moment you make that touch with the hot object, your body makes a recording of the heat that you're, I mean, trying to touch upon. Then the moment your body touches that heat or your finger or whatever it is, you will be able to understand, like, I mean, you will be able to record some amount of heat that will be captured like in your via your muscle receptors, whatever is present in your hand or in your human body. Then these muscle receptors take this information of the heat which you are touching upon. Via the muscle receptors, it will reach up to the spinal cord where the neurological information is being processed. Then there is an action potential generated with the neuron communication happens in the human brain. Then what happens? The spinal cord gives an action potential, that is electric signal, back to the muscle receptors, giving an interruption or a signal that take your hand back because there's so much of heat your body can't tolerate. Then immediately you take your finger back. So this one cycle, the moment you touch an object and within fraction of a second you take your finger back. So this action potential happens at 250 miles per hour speed. That's why with the before the heat affects your body or finger, immediately you take it back. That's why even if you touch a very hot object, immediately you take your something, your part of the body back so that you won't get hurt much. Fine. So this particular communication, whatever happened, because normally if you see the neuron communication when we're talking about, there are some dendrites like thread-like extensions, axon, we have hillock, and how the central nervous system works, and how the nucleus of the neuron is processed, the data with the help of the central nervous system. Then how the neurons communicate, what are the sensory organs, what are the motor organs, everything we have to identify. Then we are going to process the then we are going to process the data according to the requirements. So here our job is to understand such a computing model, then use it for some real-time applications. So all these things. So here we have to understand what type of functionality of the human brain we are looking into. Here our job is, see, when we are going for some brain-computer interface or any heart-computer communication when you are trying to establish, we have to understand that what is the basic functioning of the human brain. Only then we have to understand how this can be performed. Otherwise, if you don't know, for example, I'm making for lie detection type application. I don't know which part of the human brain is actually responsible for lie detection. Then obviously we will not be able to understand that. Right. Normally, brain has some cerebral cortex, some subcortical region, where first it has left. Each brain has left hemisphere and right hemisphere, where we are going to see in each hemisphere there are 4 lobes: frontal, parietal, occipital, and temporal lobes. And our job is to understand this complex behavior of the human brain in each and every lobe, and then, of course, in each and every hemisphere. And we are going to use for some real-time application. Now, frontal lobe, you see, it's not a biology class, but you have to understand some basic domain knowledge. Otherwise, you see, if you are performing some IQ testing based using brain signals, if you are performing somebody said depression or mental state analysis or stress level, somebody has answered. So when we are going to perform all these type of applications, you have to understand, unless you know which part of the human brain is responsible for what, behavior, you will not be able to take the data from the accurate locations of the human brain. Therefore, it is as bad as you are switching on and the fan and expect the light to be on. Obviously, so it is very important you should understand this behavior of each and every lobe of either hemisphere, left and right hemisphere. Okay. So just frontal lobe is responsible for organizing, planning, problem solving, decision making, emotional control, language processing, etc. Occipital lobe is responsible for certain things. So parietal lobe is responsible for spelling of words and perception, object manipulation, and similarly sense of touch when you are touching an object, etc. And Then finally, this temporal lobe is responsible for hearing functions, recognizing faces and numbers, some memory issues and all. So normally when there is a problem with some memory, people of this temporal lobe, their brain is not so active, or you can say there is some complication with the human part of the brain, where from temporal lobe is not very active. Because that recognizing faces and numbers is done by the temporal lobe, or temporal lobe is more active when we are doing this. So obviously there is some problem with that particular lobe or the region, or obviously there is some problem with the memory issues and all will come. Okay, are you following me?
Yes, sir.
Okay, so it's very important to understand the basic structure of the human brain and their behavior under each of the lobe, all four lobes in either hemisphere, left and right hemisphere. It's very, without this, you cannot make an application because you don't know where to take the brain signals from. Any application, don't think any application I can simply connect some electrode wire to the human brain and take the data. Not like that. It is not so simple. So, okay. So anyhow, I'm not going to deep into human brain, subcortical region and all that. You can just understand in case you are interested. Then what type of brain signals we can connect? When sensing the brain, when we talk about like, we can record EEG type signals, fMRI, NIRF, CAT scan, PET, many type of data we have. Like normally EEG data we have already talked about, that action potential when the neuron communication happens. Okay, so how the electric signals are being captured. These signals are produced by the nerve cells in your brain when the neuron communication happens. Similarly, fMRI, like how to detect the blood flow in the brain, just to identify some areas of activity. Uh, Similarly, other type of data, some IR light absorption when you are giving out to the brain and try to understand some particular signal behavior. So it depends on, like I mentioned, there are plenty of type of data from one connection, like brain computer interface we have. So now, if you see, most importantly, brain is located under different layers of protection. When we have, normally we have initially scalp, then we have periosteum, skull bone, dura mater, subdural space and subdural space, finally brain we have. So out of, I mean, unless you reach from among all these layers, you will not be able to reach the human brain. So obviously what happens, it is very difficult to get the actual signals, because if you see skull bone is very thick. It is very difficult unless you get accurate signal to perform a complex application with good amount of accuracy. So you have to understand how an efficient signal can be captured from all these layers. Are you following me? Therefore, there are actually two type of data acquisition process we have here. But before that, our job is to measure these action potentials coming out of the neurons by placing some electrodes on the scalp. Okay. So scalp is what the first layer. So on the scalp or on the hairs, we are going to place the electrode wires. And from the, today I will show sometimes I'll spend on practical, understanding. So here we are going to place the electrode wires on the scalp and then understanding its complex behavior, and then use it for some real-time application. Once you place the electrode wire on the scalp, then using some EEG approach like electroencephalography approach, where we used to detect the summed ionic currents, because now if you see, there are plenty of action potentials are being generated from thousands and millions and billions of neurons. So we are going to find the summed ionic currents. Okay, from these thousands of what you can say neurons, where you are going to place under a particular electrode wire. Then these signals, when they're coming to the amplifier, we are trying to amplify to around 10,000 times and then filter them. Fine. Because now you see the kind of signals that are being emitted from the action potential, or you can say the kind of brain region, they're very weak. So unless you amplify them, then it is not in a desired quality that can be captured so easily. Therefore, we have to typically amplify that around 10,000 times and then filter them. Why I'm talking about is, this is very important in the hardware configuration process. How I can connect the electrode wire, how I can take the data. It's very important to know them. Okay. So now this is known as non-invasive method. Non-invasive method, where we are placing the electrode wire on the top layer. Where you are placing the electrode wire? Tell me.
On a scalp.
On scalp. Okay, skull is the third layer. If you see, first we have scalp, then periosteum, then skull bone. Okay, we do not make any surgery. Just will place on the hairs, the scalp, you know, right? On the scalp. Okay, that is what do you mean by scalp? Just you see, if you remove the hairs, the first layer comes, no, that is a scalp. So on the scalp, we are going to place the electrode wire. Of course, obviously on the hairs, because in between there are hairs. So on the scalp, when you place the electrode wire, we are trying to amplify the signals which are being captured from that particular region of layer. But here the problem is this is non-invasive method because we don't want to make complex surgeries and all, just for simple application like lie detection. If I want to make a lie detection, can I make a complex operation and open the skull bone and then all these layers and directly connect the electrode wires to the brain? No. For simple application like IQ and lie detection, mental state analysis, I want to see the somebody's stress level. I can't make an operation or a surgery, right? So this is known as non-invasive method. But there is invasive method because sometimes I want accurate brain signals to see some medicinal application, some brain tumor related, whatever it is, some medicinal type application, healthcare type application where I want high quality signals and all, where I open the skull bone. I mean by just using by making a surgery, opening all these layers, and then because you see that there are plenty of layers covering the brain. Unless you open all these layers, you will not be able to go to the human brain, right? Obviously. So it's very, very important to understand. Okay, so that method is known as invasive method, where you're cutting the skull bone and every other layer, dura mater, periosteum, then finally you're reaching the human brain. How you are going to connect this one? That is invasive method. That is normally be performed by doctors and other medical practitioners, neurologists and all. Okay, are we clear? Now for simple application, are we going to use invasive or non-invasive method? Tell me.
Non-invasive methods.
Yes, non-invasive method we are going to use where we do not make any surgery. Simply today I'm going to show demonstrate the hardware I have. We have a separate lab here for this type of experiments at NIT Goa. So I'm going to show the lab. I mean the equipment and the electrodes, wires, and then everything which can be used to understand such a complex behavior. Okay.
So, sir, in which format we can consider the signal comes under by EEG?
Format
In which
means.
in which extension we can consider by signals of EEG?
See, once you connect the electrode wires, now it
Okay.
depends on which particular software tool you are using. For example, here we are using some 16 channel brain vision analyzer and recorder. So the first we use the recorder software. Now once the electrode wires are connected, once the signal go to the amplified signal will be stored in your workstation by after it reaching the amplifier, after amplified, it is going to your computer or workstation. That's how it make human computer interaction. Now they are in some RxT format or something. It depends on what type of software tool you are using, but they will support all these conversions or transformations. Like I want this format, I don't work, I am comfortable in MATLAB or Python. Therefore, you can convert it into a .m format or any Python file formats and all. That can be possible in the customization level once the data is recorded from the amplifier. Are you following
Okay.
me?
Okay. So in
So
Python we
initially, you
can
will
consider
consider
in
depend
.csv
on the
format.
particular software application which you have subscribed or purchased. Then, but that will definitely support to convert into some .m format or Python file format, so that you can use them again in your comfortable platform. Like I want to use normally brain vision recorder and analyzer both comes. You want to analyze at the analyzer level or you want to go for Python or MATLAB level. But recording, you have to use the recording software, same software. After recording, it is up to you. If the file format is converted to your desired platform, then you can use in MATLAB or Python or R, whatever it is, Vika, whatever it is. Are we clear?
Okay, sir. So in Python we can consider as .csv, no doubt. But during the signals comes by the amplifier, then
Uh,
we have to give some extension based on the software, isn't it, sir?
No. Here in this, but this is customized software. This is actually whatever the file format is prescribed by the developer of the software. You know, sometimes RxGDS is many formats are there. it changes because there is add instruments, there is brainwave, there is aero, there are plenty of manufacturing devices of these data acquisition systems are there. This is actually data acquisition system what we are talking about. So once the file is stored in your hard, I mean in your computer with some name, with some extension dot so and so, then you go to analyzer. I mean you go to recorder software and then convert into the you mentioned I want there is some extension file format .m and so on so Python file format and so on so then R file format. Accordingly, this will be converted into that format and final file will be in your hand. Then you can use copy paste the file and use it somewhere.
Okay, sir. Okay.
Okay. So,
Thank you,
but
sir.
the extension you cannot fix. Where in the initial data acquisition that brain vision recorder software, whatever the file format it support, that will only it will come. But after that, this whatever the file you have saved in your hard disk or external device, that can be converted into any required format, whatever is supported by the analyzer.
Yes,
Are you
sir.
following me?
Okay. Yes, sir. Got it,
Okay.
sir. Got it. Thank you.
Because mostly what happens is every time they don't want to learn new software tool. After recording, obviously we have to use. After recording, analyzer software I don't want to use. I want to do in MATLAB or Python or somewhere. Then I have to have the option. That's why when you are purchasing the software tools, you have to speak then what type of file format it supports. Then it is easy for you. Otherwise, you have to obviously learn their analyzer software.
Yes, actually, when I'm seeing some deep data set format, then they are having a lot of extension available, like .csv, .lv, these type of extension file. That's
Yes.
why I was confusing on that. By which software we are giving extension of individual file. So
See, normally, initially, whatever the file format, the developer of the software tool proposes or suggests that will be there. After that, but they will definitely support all these the regular, I mean, most of the user-friendly softwares like MATLAB, Python, R, Vika, and many others. At least this MATLAB, Python, normally they support for
mhm.
conversion. Then you are free to use in any other platform whichever you're comfortable.
Okay, okay. Thank you, sir. Thank you.
Okay. And that is a matter of 2-3 minutes, or if the file size is big, some 5-10 minutes to convert into the desired format. That's all. Okay, na? Why? Because otherwise, na, otherwise anybody can record in their desired. Then nobody will buy their software. It is like a commercial business trick that normally people used to make. If the data can be directly recorded into .m MATLAB format, then they be businesses. I mean that commercialization may not be so good. That is the reason they may be going with the customer software extension tools like that. Okay.
Yes,
So
got it.
this is a conventional BCI. I mean. Like a system setup. I mean, I don't say it's exactly BCA phases I'm showing here. I'm not showing. Like initially, this is the BCA system. There is an input which comes from subject or a patient. That is who is donating the data. Yeah, we call it the subject or a patient. Subject could be normal any application like mental state analysis or any IQ level or any other type of applications. So we call him as a subject. Somebody is giving data for some medicinal application. We call it a patient normally, subject or patient, whomever it is. So assume that some EEG type data we are taking or PIP or fMRI, CAT scan, plenty of data. Then your BCA system will be able to take the data from this subject. Then the control signal, final action potential or whatever the classified signal will be given to the front end application like smart wheelchair. Smart wheelchair for a paralyzed person who cannot control his, I mean, cannot move his limbs or legs or hands, whatever it is. He can control the smart wheelchair with his thoughts, something like that. So front-end device is the front-end application, what you're talking about. Okay. So normally like it is if you want to use for some like it's a smart controlling device based on the human thoughts and then how the device can be controlled with this behavior or something like that. So this is a typical setup, the transformation device and then everything. So there is a EEG control unit which is connected to the amplifier where the amplifier get the signals from the human brain. So it is simple. Human brain gives the signal. Signal is captured via the electrode and stored in amplifier. It will amplify to certain thousands, 10,000 times, or maybe more or less. Then the amplified signal will be stored in the workstation. There is some sophisticated softwares, customized softwares, using which you will make some analysis and take the feedback. Then based on the feedback screen, you will again ask the subject to give the recordings, and there's several cycles of recordings. Normally when you are making the recordings, we are like subject 1, that is person 1, trial 1, some gap, trial 2, some gap, like that. So from subject 1, person 1 will record some 5 minutes, then some 5 minutes gap, then some 5 minutes recording, some 5 minutes gap, something like that. Should not be continuous. You won't get accurate signal there otherwise. Then come to subject 2, then trial 1, trial 2, trial 3, and so on. Then subject 3, trial 1, trial 2, trial 3, and so on. Like that we have to manipulate here the data. Okay. It is not like that I'm validating my model on one subject under, like he say with 100% accuracy I can say somebody is lying or not. I just can't say like that simply. It is beyond that actually. Okay. So you have to validate one subject, different trials. Similarly, different subjects are different trials. Have you understood what I'm saying? In a scenario when you take the brain signal, the signal's quality may not be so good. So one subject, trial 1 data, trial 2, trial 3, and so on, several trials, some 20-30 trials. Similarly, second subject, trial 1, trial 2. So you have to take some average of these values or something like that. Then you have to consolidate. Finally, you have to validate your model on this data horizontally and vertically. Are you following me? Horizontally and vertically. Either way, you have to validate your model. Are we clear? What exactly? Because this is very important, the feedback screen, the feedback of the data recording what you taken. Then again the subject, again subjects. Then finally you will come to know the best quality signal, how they look like. Any doubts so far?
No, sir. Clear.
No, sir. No, sir.
Thank you.
Okay. So there is some online signal processing tools we have. So once the data acquisition and storage is performed, sometimes many online signal processing tools we have, then classification tools and all. That is anyhow, that's your selection level. And some biomedicine. Now we talk about some medicinal application. We have talked about like lie detection and other application. Normally, when there is a person with some spinal cord injury or any other reason where there is a spinal cord stimulation system, which we used for pain management and how to block some pain signals and how to bypass the neurological behavior or the cognition, so that the people can understand, I mean, certain things into this. So normally there are three type of brain signals we have with this neuromodulation: deep brain stimulation, transcranial magnetic stimulation, and vagal nerve stimulation. Plenty. And normally what we do here, we try to make some data recording when some kind of treatment is going on, kind of. So in deep brain stimulation, normally we try to place an electrode inside the human brain, where there is a kind of electrode wire which we used to place outside in the sense not in the nearby brain, somewhere in the inside body, but there is a particular what you can say battery pack is contact to the other side of the electrode wire, so that it can be charged and the signals can be captured in real time, something like that. Or sometimes it used to impact, or it used to uh, make active the region where it is. For example, somebody is facing some depression issues, stress issues and all. You can make such an electrode meanwhile and make such a data recordings possible, and you can understand how these disorders can be placed. But this deep brain stimulation, since you are placing the electrode wire inside the human brain or inside the skull bone, whatever it is, sometimes it is difficult to, there is some risk of infection, surgery, and all those things. Similarly, there is transcranial magnetic stimulation, where we are going to make we are going to apply a magnetic field which will induce the electric currents. When you induce such a currents to the brain, it is actually a non-invasive process. We are not going to make any surgery. Okay. This is normally used to treat some depression or to some improve your brain cognitive functions and getting some attention levels and then understanding levels and perception levels increasing, etc., etc. Similarly, to treat with migraines and all many other applications we can also talk about. Okay. So normally how do this can be performed? It's a magnetic pulse to ease the depression. How this can be done? Like it's actually non-invasive process where we try to get rid of depression with the help of this magnetic pulse that is being emitted onto the human brain. When you stimulate this magnetic pulse on the human brain cells, they will change the mood of the person, because the mood of the person is depending on the human brain. When you make this magnetic pulse stimulated onto the human brain, obviously the brain cells will act differently, right? So normally it is like a thought to control emotion and behavior patterns with the help of the brain signals, which are affected by the magnetic pulses. So these pulses, when you project onto the human brain, they trigger the electrical charges. Then by these charges, what happens? These neurons will be caused to just be active or to work efficiently. Then obviously your brain will become active, and obviously you will become active, right? Uh, Normal, this is done about some weeks time. Different type of weeks we try to perform every day some certain hours, weekly 2 to 3 sittings. Then we try to record the brain signals and going to say, after some 1 2 months treatment, we say okay, this particular region of the brain where we applied the magnetic pulse, where we stimulated, that is now becoming active because of the treatment given by this particular device. Then we can measure the improvement of the cognition. So every day you give such a treatment, and after treatment, before treatment, you take the brain signal, like that you do for 1 month, and every day you can prove that this type of magnetic pulse stimulation has increased the cognition levels, perception levels, and then improved the brain functionality. So it is something like what working on the treatment quality of these type of devices, etc. Can you see the slide for prosthetic devices? Somebody tell me, please. Neural
Yes.
prosthetic.
Yes, sir. It is visible, sir.
Yes. So here normally what happens, these neural prosthetic devices, if you see there is a person with a missing limb, maybe he must have lost in some accidents or somewhere. So now if you see previously we have a conventional artificial limbs where it can work, its performance is very limited and hardly it can replace just for normal walking, even though he cannot perform all the regular needs. But these type of neural prosthetic devices, they act exactly like a natural one almost. So here the brain signals, if you see the brain signals, whatever the action potential, I've shown some video, right? How the brain signals are being captured by the muscle receptors, how the action potential is being emitted, and then reach to certain level of execution. So similar way, when there is action potential is unable to reach because after certain level of body, after certain location of the body, the limb is missing. Therefore, there the electrical signals end. The muscle receptors which are carry forwarding the action potential. So thereby you can bypass the signals by placing some electrode wires, and then use this particular cognitive behavior which is captured to control this type of robotic arm type device, or you can say some smart prosthetic. This is a prosthetic leg. What is shown in the slide is a prosthetic leg, and you can use and you can develop these type of devices with the help of brain signals. So according to the brain signals, it can walk, it can capture, it can walk, it can stand, it can do all the possible actions. You can decide what type of moves you expect from the artificial limb which you are placing for some desired purpose accordingly. So how the impaired nervous system which can be used, how they improve the functioning of a device with the help of the brain signals, and how to control the prosthetic device when there is a loss of limb. This is one of the, and is it not a kind of a good IoT device? Is it not an IoT device? Somebody tell me.
Yes, sir.
Sir, can you repeat question, please, again, sir?
Is is it not an IoT device?
Yes, sir. It is IoT device because a lot of sensor we are using for putting on for
Yes,
measuring the.
different sensors, different data recordings you are making, you are controlling. There is a processor, there is some Arduino or Raspberry Pi. You can use any microprocessor, microcontroller. You can control from this thing. So it's a smart kind of IoT device for some biomedicinal application like this. Okay?
Yes, sir.
Now, this performance is not like the conventional artificial devices, processor devices which use. This is neural processor devices. Directly, it is controlled by the signals from the. Now, if you see conventional one, normally they have no energy source or they have no. You have to lift that one. You have to bear the pain of that one. You have to the weight of this. But when you go for neural processor devices with the brain signals, it can have the what you can say. Energy efficiency type application. You can have many other mainly it is user friendly compared to other conventional processor devices. Similarly, retinal implants, when we talk about this type of retinal implants, normally they work with different other automation type. Okay, so this type of devices, what we do normally, if there is some artificial I mean if there is some problem with the vision, there is some artificial chip can be placed, and then whatever the scenes that are captured by using the artificial lens, and then which are stored in the chip, that is normally be connected to the optic nerve, because optic nerve is directly connected to the human brain. So when the optic nerve is directly connected to the human brain, if we can make such a bypassing or interface where the images that are captured by the artificial lens are stored in the optic nerve, then we can solve many people vision issues. But the question is, still some we are only into preliminary level. Still, the research is going on to make such a retinal implants which can improve the vision perceptions and all. But it takes there's a long way to go. But this is also kind of a human computer interaction device which are there are plenty of problems with the neuroprocessor devices. There are a lot of applications also, advantages also. The input output is non-linear, obviously, and the position of the electrode wire is very important. Accordingly, the quality can be identified. Then reprogramming on startup. Every time when you are starting, you have to. I mean, when it restart, you have to adjust with the scenario, and again we have to work according to the performance. Then speed of information transfer is one of the major problem. When you are walking, it is you are walking on real time. When the left leg is moving one, right should take one. So it is not like the left leg is moving two times, right leg is moving only one. Then obviously the person will fall down. So the speed of information transfer to capture such a brain signals, and then accordingly the processing devices can work, the neural processing devices. It is very important to balance or to maintain such a speed of information transfer, particularly in retinal processing devices. Because you are walking towards a wall, you should not be alerted after hitting the wall. Okay. So similarly, feedback delay, lack of precision, and then poor signal quality. If the signal quality is poor sometimes because of some amplifying issues or any other, whatever it is. So similarly, there are some plenty of people have used these type of processing devices, and the one that is shown in the figure is the first woman to receive an implanted neural processing devices. Which made her to perform certain tasks despite of paralyzed lower limb she has. And similarly other examples. Now if you see this type of behavior from the human brain, like EEG type signal, EMG, fMRI type signal, they have been captured long back. I mean, they have been identified long back. There is some kind of magnetic field that is being captured, some kind of electrical field around the brain. So this signal reflecting was identified long back in 1929 by Hans Berger, but still we are working on that. But in the early days, it was not so popular because of the computational limitations. Because that time it was difficult, very difficult to capture such a signal on real time, or in a normal scenario also even, and deal with them, analyze them. But now it is completely, because with the increasing growth in the artificial intelligence and big data analytics, people started working on petabytes and exabyte of data information. where they can capture easily all this complex signal and understand the human brain behavior. So now it has become impossible because of the evolvements in the computing world. So like I mentioned already, it is very important to understand the domain here, because unless you know you're working in brain computing, unless you have fair idea about brain and different brain signals, benchmark behavior, you will not be able to perform any good application. So you should know what type of different benchmark behavior that comes from the human brain. Are you following me? So normally what happens, alert, when somebody is alert, see, if you see, we should know exactly the different popular, or you can say well-known behavior from the human brain, so that you can use this complex benchmark signals or behavior when you are working on some real-time problems. For example, when somebody is alert, normally we see beta waves. They look like that. Similarly, when somebody is relaxing, we have alpha waves. When somebody is sleeping, we have theta waves. When somebody is relaxing, we have different type of waves. When somebody is in deep sleep, we have delta waves. And similarly, if somebody is in paradoxical sleep, that is nothing but sleeping, dreaming. Paradoxical sleep we call as dreaming, where we used to get REM type signals, this type of behavior. So it is very important to understand them and then go for recordings of the brain signals for the selected application. Are you following me?
Yes, sir.
So here, for example, if you take alpha beta, can you give me one application where I can use this type of signals? Tell me.
Yes, sir. In stress identification of stress level, we can use whether the
How to identify stress using alpha beta waves? Please
Sir,
alpha
when we are
waves, whether the person is relaxing or not for a
no,
certain
no, no,
amount of
sir.
time.
Sir, when we are solving puzzle type of problem, that will comes under the gamma waves, I think, or alpha wave means some relaxation below from the beta, gamma then beta then alpha. Okay, so when we are sometimes feeling relaxed, then again sometimes solving some problem, that type of wave comes under the alpha wave.
Okay, see, for example, just just for discussion, if we talk about alertness, like I want to see like somebody in the class, how many are alert. If you can develop some kind of wearable device, like I want to see in a class when the faculty or teacher is teaching, how many students are alert. So if only alpha waves comes, like they are relaxing mode, they are not alert, they are not following the lecture, something like that. But a better application could be using alpha beta waves, like safety driving. Safety driving. Can somebody guess how we can use for safety driving using alpha and beta waves, or alpha, sorry, and beta and theta waves? You tell me.
Driver drowsiness application, we can use whether the driver is feeling
Yes, so
sleepy or
you
not.
can develop just a wearable device,
Yes,
smart,
yes,
small wearable device, and place like smart cap or easy cap type application where the driver can wear the cap on the head. Then when he is driving, the cap will record the brain signals. If theta waves comes, theta waves are recorded. Can you expect the vehicle to be on?
no, it has
No,
to.
because when the theta waves are noted by the wearable device that is capturing the brain signals on real time,
Then
when
it
this
has to send some alert or something.
yes, so if you can integrate this particular wearable device by Bluetooth to your vehicle, because every vehicle has a processor, obviously, right? So if you can interface these two, then obviously if there is a noting of theta waves come, once you note the theta waves means he is sleepy or drowsy, whatever it is, then accordingly immediately you can alert the vehicle not to start or immediately stop and ask the driver to relax and take rest, and then again he can start after some time. So it is like a not as a voice assisted type, but it's an automated vehicle management system where you can control the vehicle based on the emotions of the driver, based on the brain behavior from the driver who is driving the car, etc. Normally, when you are driving a vehicle, which type of waves you expect to tell me when you are driving?
Gamma wave, sir.
Beta waves. You see, you should be alert, right? When you are
Beta
driving,
waves.
you should be alert. Beta waves. So normally the driver should be alert. Beta waves in between sometimes when there is no much traffic, relax a bit. So maybe beta alpha coming interchange, right? So mostly it is like a beta waves in between something. You all agree?
Yes, sir.
So but if you have theta waves comes, that should not be allowed because when the driver is driving, there should not be theta waves. Please turn up your microphone some. Yes. So there should not be any presence of theta waves, obviously. But beta waves normally we expect because driver should always be alert when he is driving. Sometimes when the road is very smooth and then there is no much traffic, maybe he can relax in between, but still he is looking after that. So maybe beta waves and alpha waves can interchangeably can come, but mostly beta waves he has to emit when he is driving a vehicle. Okay. So these type of delta waves and theta waves. Of course, you're right.
Sir,
Delta waves
okay.
also. Theta waves and delta waves when they are emitted when somebody is driving the vehicle, obviously we should not allow. And many other type of application. This is just an example. Tell me any doubts?
Sir, is there any gamma waves also available in EEG or not?
Gamma waves, I think they are available, but for exact behavior, I am not remember.
Okay,
Only these
actually,
are there are plenty of other waves. This is just a benchmark, just an example I am giving. Similarly, plenty of other examples in the coming slide. There are few more I am going to discuss. I think gamma.
actually, yes, sir. Actually, I saw one paper in that gamma wave was also available, and for measuring that, we saw the example like puzzle type of problem. When someone is solving puzzle type of mathematical type of problem, then
Yes.
that type of waves will comes under the
It is
gamma
there.
wave. That's
There.
why.
I'm not telling only alpha, beta, delta is just plenty of there. Just an example I'm giving. Now, when
Okay,
somebody
sir.
is crying, when somebody is laughing, when somebody, there may be different type of behavior.
Okay,
Because
okay, sir.
brain
Okay.
behavior, the cognition is different from emotion to emotion, person to person. So obviously it is different. So there is
Yes, sir.
different type of waves are there, but just still I don't remember exactly what is for gamma, but I have to see. But it is there maybe.
Yes, sir. Okay, thank you, sir.
Right. Now, similarly, paradoxical sleep. Now, see, if you go with the application paradoxical sleep. Now, if I ask, if you have had a dream in the last night, okay, can anybody else say that you had a dream last night other than you?
No one knows.
No one knows, right? Unless you say.
And yes,
So, only you knows that you had a dream the last night.
yes, sir.
But where in case if I ask you, because you know that you had a dream, if I ask you what time you had a dream, can you say?
No, sir.
No. Hardly next day morning when you wake up, you can say, yesterday I could not sleep well, I had a lot of dreams, something like that you can say. But you don't even remember what time you had a dream, right?
Yes, sir. Yes, sir.
But if I say, if I connect the electrode wires to your scalp or brain, or I mean to your head, before you go to bed, next day morning I can say that you need not to say. I can say that if I note that dreaming signals, paradoxical sleep, REM signals, I can say next day you had you had a dream. You had some two dreams, sometime 3 a.m. to 4 a.m. or some 1 a.m. to 2 p.m. or 2 a.m. Even I can say the time exactly. Is it possible?
Yes, sir.
Obviously, because the moment you see the what time with the time, if you compare the presence of these REM signals, you'll definitely able to say, okay, this time it appears like this type of waves are seen, which means you must be having some dream last night. So this type of paradoxical analysis, dream analysis and all application. Just an example I'm telling. Why I'm telling is you should understand the in depth what is the behavior of human brain, what type of different waves can be emitted when the person is of different emotions. So only then you will be able to perform a complex operations like this, right? Fine. And then this is just an example. Similarly, dream analysis and all. Similarly, many other applications also one can perform. So now this is in detail beta waves, how alpha waves, which location they occur. and what is their ranges and frequencies, etc. So tell me how many lobes we have in the human brain?
4.
There are 4 lobes: frontal, parietal, occipital, and temporal lobe. But there are 2 hemispheres, left and right hemisphere. Each hemisphere has 4 lobes. Okay, but they are of same type actually. So altogether there are 4 lobes, but they are partitioned into 2, left and right hemisphere actually. So left hemisphere frontal lobe, parietal, occipital, temporal. Right hemisphere frontal, parietal, occipital, and temporal. So beta waves normally of range 13 to 30 hertz, which occur in frontal or parietal lobe normally. Okay, wherein alpha waves, which usually occur in occipital lobe with a range 8 to 13 hertz. Wherein case theta waves usually occur at the range of 4 to 8 hertz and normally occur in children and sleeping adults. Similarly, delta waves 0.5 to 4 hertz and then occur normally in infants normally and some sleeping adults. Similarly, other type of waves, some epilepsy, when some other type of problems comes, these type of waves with 3 hertz and fixed bandwidth and fixed range. So it's very important to understand such a behavior and then use it. So there are similar people who have used these type of applications, human-computer interaction, and they communicated with the real-time world. They communicated with the real-time world, and then they have done this type of application. How much time we have? Please confirm.
Sir, actually from 11:30 to 11:40 we have break, sir. 10 minutes of break. Again after that we have 2 hours of sessions.
Okay, so now just 1 second. Then we will. Okay, anyhow, just after 5 minutes we'll conclude, and we will
Okay, sir.
resume the session after this. No problem.
Okay,
So
sir.
this is the entire operating environment. This is the entire operating environment of the your brain computer interface when we talk about. Normally here what happens, there is a BCA control unit where see, first we start with the subject where we are placing the electrode on the human's scalp or when we're talking about brain computer interface. Then the user signals, I mean the one who is donating the signal, the subject or patient, the signal will go to the amplifier. The amplified signals, filtered signals will go to the BCA control unit where there is a feature extraction, feature translation happens. Because after normally how to do any data mining issues when you take data after pre-processing, feature extraction, classification we make, right? So when the once the amplified signal or the filtered signals gives from the user control to the BCA control center, BCA control unit, their feature extractor and feature translator will be there. Subject to the requirement, sometimes some feature will be extracted, some feature will be translated. Then it is connected to the control interface. Control interface with this control interface. Normally, what happens? There is some external simulator control display with the data that is being captured from the human brain. Then the control interface will see how this particular featured signals can be used for classification, and then finally what happens, these control interface will give a semantic control with the available input signal based on the classification results. So finally this device control will have the final output. So what to do based on the signal, so it will give an indication or some kind of potential or some kind of interruption to the smart wheelchair or smart device based on the features and the classes, whatever the data we have extracted from. Okay, so this device control will take the feedback every time and then update based on the brain signals. Okay, because every time we are taking a feedback, it is a continuous. Finally, once the device is functioning accordingly, again we are going to take the data and one more round of cycle. Again, it will go to see the device to user. There is a device feedback we are taking, and again user is giving the signal. Finally, we are streamlining. We are refining the signal quality and over the time, and finally the amplifier is giving a better quality signal and better features are coming and better classified signals are there and better device control can work accordingly. Are you following me?
Yes, sir.
So this is the entire operating environment and how these signals can be used and captured for the real-time analysis of the behavior of a particular application. Now in this example, the one that is shown is for smart wheelchair. There is a smart device wheelchair for the application like this. Then the operating environment can be again repeated for different users or different trials. Same user, like I mentioned, same user now after seeing the feedback from the device controller, then again you can see another trial for the same subject, then trial 3 from the same subject, and so on. Finally, different trials for different subjects. So that's what I'm telling. Horizontal and vertically, we are going to talk about this type of brain behavior, how we are going to capture that. Okay, are we following?
Yes.
Okay. So, one second. I think how many slides are there? Okay, I think we'll stop here and we'll come back after 10 minutes. Next 15-20 minutes I'll finish because we have small hardware thing also there. We cannot finish in 5-10 minutes. So we will come back and we'll start with the session. Then we'll go to the applications.
Sir, sorry for interrupting, sir. Can you see some practical implementation of this?
I will show now after this.
Okay, sir. Thank you, sir. Thank you.
Now I have now since this is virtual, I will show some recordings. I will show the hardware. First I will explain the hardware, how it can be used. Then I will
Okay.
show some recorded videos which you can understand. Okay.
Achha, okay, one question from my side, sir. Sorry
Yes.
for delay. Actually, when some noise will come during these different type of waves, then what we can do for minimizing that?
Now see, there are plenty of noise removal or artifact removal template. These tools will be there in the Brain Vision Analyzer and the recorder softwares which you are recording. So they automatically what you can say, try to avoid all these artifacts or noise by default. And still, if you want to propose some, this is there are plenty of filters, notch filter, low pass filter, band pass filter. There are plenty of filters already exist in the tools. So there are customized tools are already available for that. By default, because there will be in the non-invasive mode, there will be a lot of noise already. So obviously we are going to have a lot of noise that can be deleted by some inbuilt filters. Now, if you don't want that filters because your type of data is different, the type of signals are different, the type of spikes may be identified, then you can propose your own filters. Okay, so you are going to use some filters and some noise removal or artifact removal techniques before you are going to make the feature extraction or classification. So whether you use the existing built-in filters or you propose your own filters, that is up to you. Are we clear?
Okay, sir. Okay, sir.
Today I will show after, see, with noise, without noise, how it is. After this break I will show.
Yeah, thank you so much, sir. Thank you so much.
You know? Since it's 1.5 hours, now we'll take a short break and we'll come back. Okay. Lavanya madam, how much time we have?
Sir, 10 minutes of break, sir. We can rejoin by 40, sir, 11:40.
Okay, fine. No issue.
Thank you, sir. Thank you.
Right. So we'll join after this.